scared me too.
I'm not scared. I'll be on. Yeah.
What about?
All right. How are we doing?
Are you doing that?
A little bit. Actually, I don't feel too great yet, but better than I was last week. Last week I couldn't function at all.
I guess we're lucky it's a week long.
Yes, exactly. But we are planning on out there tonight. Looks nice. We're gonna play around with taking pictures. Oh yeah, and kind of just messing around a little bit. This weekend, I'd like to do that probably next week too. If it's nice and clear. Forecast is good. This has been the best fall we've ever had, so you guys are having a good time.
Nice.
Then the next one after that is the one right before Thanksgiving, the Monday before Thanksgiving. We will not go out to the observatory because it's gonna be a full moon. So no matter what, we won't go out to the observatory. And we'll see, we may or may not, we may just not even have a class, depends on how much I get through this week and next week. Meaning if I get through enough material, then we might just take that Monday off. All right, then we come back and we got 2 Mondays. The first one we'll do, we'll review, and then the last Monday we meet is the final. Okay, now part of the final is going to the observatory and you get graded on setting up the telescope and finding objects. Where you have to do it all right, and I'm not gonna help you, and I check you off, and I'll give you a sheet of what I look for. Has to be focused, centered. This seems to be our biggest problem.
Is
Yes.
that gonna be by group?
Yeah, by group. So you get a grade for the group. That actually ends in as part of your final for the class. And also remember, a huge part of your grade in this class is your notebook too. So that'll be due the last day of class. When you take the final, you turn in your notebook at the beginning, right before you turn to take the final. Okay?
So I'm guessing it's gonna be an hour and then we go to the observatory?
Well, we may do it the week before.
Oh, right, okay.
We can do that whenever we go out to the observatory, either the week before or that day. So one of the two has to be clear.
So this is our last day in the class and one for the final for those meetings?
Yeah, so if it's not clear the week before, where we can't go out there, we'll take the final and then we'll go out to the observatory. Which isn't fun, but we do what we have to. If it isn't clear the week before, which I'm hoping, then we'll go do that part and have that done, and then you take the final instead. All right, tonight, I want to talk a little bit about atmospheric effects. Our problem is we live on a ball, a sphere, the outside of a sphere that has an atmosphere. Yeah, it's a problem. Well, it's not really a problem if you're trying to breathe, but it's a problem if you're an astronomer because the atmosphere affects the light, starlight coming through. So in our extremely exaggerated situation here, here's Herb. Okay, and that's the atmosphere. Remember, this is not anywhere close to scale. Because really to scale, you show the whole Earth, and then there's this thin little line you can hardly see. Because our atmosphere is only about 50 miles thick, compared to the 3,000, 5,000 mile diameter or radius of the planet. So it's really a tiny, thin little layer around the edge. We think of it as thicker because that's where we live, but it's really not very thick relative to the planet. All right, we have we defined something called the air mass. It's essentially is how much air you're looking through when you look at an object. I'm missing something. Oh wait, we're missing glowing, aren't we? All right, when you look straight up at your zenith, an object has an air mass of 1. And for astronomers, air mass is usually designated with a capital X. Not sure why, but that's just the standard. However, you notice if you're looking at a star that's like over here, you're looking at it. This distance here is a lot further than that distance. So you're looking through way more atmosphere. And the angle between here and here, this is called your zenith angle. Now your zenith angle is exactly complementary to what angle? Remember what complementary means?
90.
They add up to 90, right? So zenith angle is measured from the zenith this way.
Right.
We don't call it height, we call it
Altitude.
altitude. So altitude and zenith angle are complementary. They add up to 90 degrees. Okay. All right, so what we really want to know is how long that distance is. If we call this side 1, can we figure out what this side is? Using your zenith angle?
Yes.
How?
Three.
Yeah, use some trig. What trig? We're gonna call our zenith angle Z.
Adjacent.
So you're gonna use cosine. What does cosine of Z equal?
Cosine of Z.
Yep. Z is our zenith angle.
Oh, that's cosine of 9.
1 over.
1 over the air mass, right?
Did it bounce out?
No, it went off the edge. There was a little gap between there and I still hit it. All right, so the air mass is actually equal to 1 over the cosine of Z, right?
Yep.
What's 1 over the cosine?
That is between 1 and 3.
I think it's a cosecant of Z, right? Or we did it as altitude. It would be I'm testing your trig skills here. Altitude is this angle right here, right? How far above the horizon?
So you do sine.
You do sine. So it'd be 1 over the sine of the altitude, which is secant.
1 over cosine.
Yeah. Or did I do that backwards?
1 over
No,
cosine.
yeah.
3 to 2.
Yeah, that's secant.
Did I go backwards?
Yeah, that should be a secant.
That should be secant. Yeah, who did cosecant? This is secant.
The other one is cosine.
The other one is cosecant. My trig needs to be a.
Yeah. It's not the same thing, but you just did the other side differently.
Yeah, you're just using the opposite angle, right? The reality is that nobody uses cosecants and secants anymore anyway, because they're not on your calculator, right? So most people just write it as this. Okay. However, that's not very accurate. Why? Because that would say if our zenith angle is 90, right here, right? What's the cosine of 90?
0.
Yeah, what's 1 over 0?
Oh.
Infinite. That would say you'd be looking through an infinite amount of air, which would only be true if we lived on a flat Earth. Don't tell those flat Earth society people, but we don't live on a flat Earth. All right. In fact, you're going to be able to prove it yourself if you go out next week. What? There is a lunar eclipse next week.
Ooh.
Now we used to, sometimes we open the door, we decided not to do it for this one. But I recommend you go out and look at it yourself. It's going to be, I think it's Friday morning, at about like 2 or 3 in the morning.
No.
And it's not completely total, but it's like 90 some %. So It'll still look cool. It'll turn red. Full moon will look red.
This Friday?
No, the 17th, 18th.
Okay. I was wondering.
I'll remind you again next week, but put it on your long-term calendar. If you haven't seen, how many people have seen lunar eclipses? Well, yeah, okay. You should see them. They're just cool. They come every few years, so it's not real rare, but that's coming up. All right, so air mass, mostly we do is one coefficient, but I want to give you a better approximation, because we can correct for the fact that the Earth is curved. And as you look further and further down towards the horizon, the air actually bends starlight. It refracts the light. So when you see a star that's down here, the light actually comes up, hits the atmosphere, and then bends around to you. So you can see things lower than you actually should be able to. The refraction effect. So this is only good up to a point. What we really want to do is say that our air mass, remember our air mass is x, the secant of z, 1 minus 0.0012 secant squared z minus 1. Or if you want to write it so it's easier in your calculator, the 1 over cosine z, 1 minus 0.0012, 1 over cosine squared z, that's 1. Since you don't have a secant in your calculator, I think most of them don't. I think some of the inspired might, but they have everything, you just can't find it.
So what's the unit for air mass?
There is no unit. Like what? Yeah, because we arbitrarily set this equal to 1 air mass, right? And so really it's just a ratio comparing. So if you get over here that this is like 2, it just means it's twice as much atmosphere as when you're looking straight up.
Is it mass?
It's not mass.
Okay. So literally.
It would be a length really,
Oh, okay.
but it's relative. So it'd be just 2 air masses. So I guess the unit is air mass. All right?
If you calculate the total mass of air and then
Yeah, but it's not really mass because remember air mass doesn't really work because mass is a unit of matter, right? Well, there's more mass down here than is up here because the atmosphere thickness gets less as you go up. So yeah, changes things. All right. Now, why do we care? Because we already talked about as you look through more and more atmosphere, you run into several effects that occur. Okay, these are effects. We have extinction. And transformation. Extinction means that you're looking through more air and the air actually disrupts the light, so you see less and less. So stars you can see up here, when you get down here, you can't see them. So if you see a faint star up here, if you're trying to look at it when it's real low, you won't even see it. The light doesn't penetrate the atmosphere to get all the way to you. So that's extinction. Transformation is a color change. As you look through more and more atmosphere, the color of the stars and objects changes. Same way with the sun. Everybody's familiar with the sun. When you get to sunset, does the sun look the same color as when it's up here? No, it turns red, right? Why is it turning red? Is it sun changing colors?
Red light is scattered less.
Right, the blue lights get scattered out and makes our sky blue. Why? What's the difference between blue light and red light? Wavelength, right. So the shorter wavelength gets scattered more by our atmosphere than the red light does. It's preferential. So we get a blue sky. Okay. It also means that we get red sunsets because the red light can penetrate through, the blue gets scattered out. And the effect is bigger, the greater the air mass. The more air you're looking through, the bigger the effect. Yeah. All right. So
Can you repeat what extinction was again?
extinction is the dimming. So I should, yeah, make this clear. Dimming of light toward higher air mass. And it's a color change towards higher air mass. Yeah. I have a sheet here. Kind of shows it. The problem is, it was in color and I ran it off and it's not in color, so you can't see how nice color. Imagine you're colorblind and it's be perfect.
I might.
Base areas like this and even if you're missing future.
All right. The other thing before we get to this, just hold on to that second. I want to talk about seeing. Seeing, yeah, this is the word astronomers created for the fact that sometimes when you go out, you see the stars, they're really crisp and you can see them really well. And then sometimes you can look at the same stars and they're kind of all blurry and fuzzy. Seeing is kind of a catch-all thing for how much the atmosphere is messing up the viewing of stars. Okay? In fact, astronomers actually can measure this. We measure something called the FWEM,
Oh,
which stands for full width at half maximum. When starlight comes through space, here's my star. The starlight coming from space is a perfect point source. The stars are so far away, you can't see a disk. In fact, I think there's only like 2 stars in the whole sky. There's an actual disk there. Because they're so far away, they're just points.
Which one?
Betelgeuse is one, because it's big enough. And I think it's another red giant, I'm not sure which one. Where they're big enough, then close enough that there is a disk, we just can't really see it. But once it hits our atmosphere, that light gets spread out, and a typical star then looks actually like this. It's a Gaussian shape, it spreads it out. Okay. And what we do is we say, okay, let's take the full width at half maximum. So maximum, you just go right down the center and say, oh, half the maximum. This right here is the full width at half maximum. The cool thing about that is if you have a brighter or fainter star, so if you have a fainter star, it would look like this. But at half maximum, the width is still going to be exactly the same. It doesn't matter whether it's a bright star or faint star, that width, because of the way light spreads, will be about the same. Now, if the seeing is really bad, if there's lots of turbulent air, then what happens to that same star is instead of looking like this, it now looks like this. The light gets spread out more. And then when you measure it, the width is significantly larger. And I've been saying all semester that we measure our seeing, or the quality of what we can see, we measure it in arc seconds. The best observatories in the earth get about 1 arc second seen. Just remember, it's about 1/3600th of a degree of detail. You can't get any better than that from Earth without using fancy stuff like adaptive optics, which is what they do on telescopes like the Keck telescope. They just shoot a laser into the air, they see how the air moves, and then if you move it exactly the opposite, you correct for that, and you can make it even better. It's the same idea of noise canceling headphones that is done with light. Super sophisticated, but it works. They're really good at it. Okay, but for most of us, that never happens. Around here, we never even get close to 1 arc second. We're not on the top of a mountain. We're not out where there's no light pollution, other pollution. If we get to 2 arc seconds, so in commerce, the best we ever get is maybe 2 in the middle of winter when it's real cold. Typical is around 3. Just the way it is. Okay? And in the summer, it's even worse. You throw in things like humidity and dust and all that, and it gets even worse. Our best time of year around here is fall and winter by far for quality of seed. When you're up on top of a mountain, doesn't matter as much time of year, it just matters what the weather is like. Lots of times, the best time is right after a cold front comes through. You have all these thunderstorms and all the nastiness, and it gets real cold. Well, that brings in really cool, dense, steady air after it. And that's usually the best time to observe, is right after all that wipes through this. All right, so seeing is a measure of the spread of a star caused by the light coming through the atmosphere. All right. Now we can measure the scene and how it changes as a function of air mass. So we have an equation here. Make sure I get the power right. To the 3/5 power. So this is the scene at the zenith. This is air mass, of course. And this is the scene at that air mass. So if the scene at the zenith is 1 arc second, so it's really good straight up, it's still going to get worse as you go down. And if you get to zenith angles 50, 60, 70, all your stars are going to start to get wider and fuzzed out. That's why we don't like looking at things that are real low in the sky, because they just don't look good. All right, so how does that show up on here? Well, if you look at here, this shows essentially this is that plot. This is a plot of a power of the to the 3/5 power. You can see the scene as a function of. They did it in altitude. Okay, so don't get confused. Altitude and zenith angle, remember they're complementary. But as you get closer and closer to the horizon, then your seeing goes bad. Okay? And you notice that the red, green, and blue, the light, because our atmosphere actually splits it apart, they refract at different rates. And so the red has the least effect, which is why we have red suns at 30. Blue has the greatest effect. So as the star gets closer to the horizon, the red, green, and blue will separate out. You can't really see that. This is the chart that's supposed to show that. So when you're looking at a star straight up here, it looks nice and white. As it gets down here, it starts to have red and blue shimmering back and forth. And lots of people will see horizon, a star close to the horizon will be twinkling like crazy. That's the atmosphere. And it'll be changing colors. And I think it's a UFO. And I go, no, it's just the air was really bad last night. They don't realize how much the air actually affects it. Same thing for planets and other objects too, not just stars. Now, the disadvantage you have with a planet is the planet's actually a disk, not a point. So what happens with a planet is you don't see the planet move around or anything. But what you see is it gets fuzzy and clear and fuzzy and clear. That's why you probably notice that when you look through a telescope, you're looking at Jupiter or Saturn. You just kind of stare at it for a while and it'll get real crisp and then it'll kind of fade in and out. That's different waves of air passing through. So amateurs now that take really nice pictures of the planets, they just take thousands of them. And then they throw out all those ones that were bad and they just pick out the ones that just happen to be really good. Because the light coming through the atmosphere, you know, even though it's bouncing around, every once in a while, a nice crisp one will come through. Or you just pick out those and add them together, you can make a really great picture. So it's kind of a tricky thing to do, but it does work. All right, so that's the effects. And that's why the atmosphere is a problem. It's because it causes all these problems. Now, if you're doing research in astronomy, and you want to say measure the brightness of an object as it goes across the night sky, that brightness will change just because you're going from high air mass to low air mass to high air mass again. Now we correct that out so that that doesn't affect what you're measuring, but you have to correct for those kind of things. Okay. All right. Questions about that? Let me show you if I can make this work. Some example pictures. Yep. Maybe. It is not working. Come on, dude. It's supposed to work. Sorry, I haven't used this before, so I don't know why. Being unfriendly. It's the wrong computer. Okay. Well, there's only one. So it's supposed to be that HDMI 1 is this computer, and then when you put in an external one, it's supposed to be HDMI 2, but obviously that's not pretty. I got one more option I can try here. Not gonna let me do this, I don't think. Well, sorry. Some days I want to be cooperative. All right, well, fortunately, That is not working well for me. That's why I want to show you pictures. That didn't work. We're doing it the old bed. I think that the observatory will work better. All right, so these are two pictures of the same star field. If you look over here, this one has really bad seed. This one has really good seed. You see the difference here? You can see tons of little stars. Yeah, they are negative. Okay, which is the way we usually do pictures because it makes the star show better. But you see here, the little faint stars just go away. And even the big stars are kind of big round things. And then here you can see all the details of the little ones. The biggest challenge, and we'll mess with when you're taking pictures tonight, is getting a really sharp focus. The focus occurs when you get the star as small as you can, right? The tiniest point source means you have the best focus. That is always the hardest part. And if you see here, I'll show you here. This is the difference between the star profiles. Like I was showing you the star profile, this is just half of it. So lots of times they do half. But you see here, this is good seeing. If you went down to half width, the seeing would be really tight, where here the light is spread way out. And we call that full width happening. When you're observing, when you're actually using telescopes, you actually record that and see how it changes as the night goes on too. Depending on clouds and weather and stuff, it actually just changes during the night. It also is affected by your telescope. If your telescope, like early in the night, your telescope might be warmer than the air and then it cools off. It'll get better as it cools off. That creates internal turbulence, has the same kind of problems. All right, one more picture I want to show you if make this work. This is the difference between seeing Jupiter in good seed and bad seed.
Oh, wow.
So this is good seed. This is bad seed, obviously, right?
Yeah, that's right.
Yes.
All right. You're saying we've never seen good seed, have we? All right. Now it's the same thing as if you stare at Jupiter for a while, then it'll kind of fade in and out. Okay, so when you look at Jupiter through the telescope, don't just look real close. Just watch it for a little while. It'll fade in and out. So the other thing is you gotta get the focus perfect. So then you gotta let go. Because if you're touching the telescope at all, you're causing vibrations you're making just like bad seed. So you gotta kind of let it settle down. You gotta focus and then just let it settle down, take your hand up. Same thing with taking pictures, is you don't want to be touching the camera, the telescope, or anything when you take pictures. Because any touch at all is causing vibrations. And when you're talking hundreds of a degree here, a few arc seconds, it shows up. So that's why all our telescopes are mounted in concrete and pillars, so that you try to make it as stable as possible. All right. All right, never got that to work the way it's supposed to, but that's life. Here is the homework. You're like, oh, I've been missing homework.
I have been.
It's been what, 2 or 3 weeks since we had one. And let's head out to the observatory.
Yeah,
I can get some more, yes.
I can see a little more. You have a 4, right? Or a 2 on Wednesday, Wednesday, Friday.
I think I might have left them out at the observatory, but I will bring some just in case. And I'll see you out there in a few minutes.
I've got time between, I have 11 to 12:30.
Oh, yeah.
Yeah. And then an hour after that I could stay.
I like that.
You guys want to-
No.
Yes, I think